This is AS2 Physics 2, June 06. Number 2. A slinky spring may be used to demonstrate the behaviour of a longitudinal sound wave. Explain what is meant by a longitudinal wave. So you've had this question a couple of times before already. And so this is a wave where the particles vibrate. And they vibrate parallel, to the direction of travel of the wave, or the direction energy is moving. Figure 2.1 shows an instantaneous picture of a slinky spring which is vibrating longitudinally at a frequency of 2 Hz. The positions of maximum compression and maximum rarefaction are marked with the letters C and R respectively. And you can see here there's a slinky spring, there's compression, rarefaction, compression, rarefaction, compression. On the axis of figure 2.1, sketch a graph to show how the displacement of the coils of the spring from their mean position depends on their position along the slinky. So you know that, or you should know that, in the centre of a compression, the centre of a rarefaction, all those particles are at rest. So I'm going to make a wee dot just directly underneath each compression and rarefaction. Now you can see in the compression that most of the coils would be fairly close to that centre position, here, here and here. But in a rarefaction, you're going to have your maximum displacement from its rest position are going to be some of these coils in the middle here between, they've moved out, and I'm going to put a wee arrow, moved out the way from the rarefaction, like that. Okay, so some of them have moved left, and if we make left a positive displacement and some of them have moved right, then it's a negative displacement, so plus and minus there. And so you can see that the ones which have moved the most would be correspond to here, and then most in the opposite direction, most in this direction, most in the opposite direction. And you can see there you're going to get a sine wave when I join these up. So if I just join these up here, and so you can see that it's these particles on either side of the rarefaction which have the maximum displacement here and here, and the ones near compression are fairly close to the middle, so they don't have this maximum displacement. You know, if I look up there and here, you can see that all the compression, the particles that are in the compression are only displaced by small amounts from their rest position, but it's these particles in the rarefaction which are displaced by the most in the middle of the, or the edges of the rarefaction. They've moved out the most from their centre position. Mark on your graph in figure 2.1 the amplitude A0 and the wavelength lambda of the wave on the string or on the spring. So amplitude then is going to be the distance from the rest position to the top of a crest to the bottom of a trough. We'll mark this one here, and it's called A0. And then the wavelength lambda is from one position on one wave to exactly the same position on the next. So we'll maybe mark from there to there. And if you look up at the diagram, you can see that that would be from the centre. Well, I haven't marked it on there, but it's from one position on one wave to the exactly the same position on the next wave. So these two here are doing exactly the same thing. It maybe would make more sense there to do it from a crest to a crest, or from the middle of a rarefaction to the middle of a rarefaction. So that's one complete wavelength. The last part of this question, the distance between a compression C and the adjacent rarefaction R on the spring is 14 centimetres. So we'll have a wee look at that. That's really just from there to there. Now you can see, if you look down beneath this, that that is from there to there, which is only half a wavelength. Sorry, can't see that, okay. So from there to there is from there to there, which is half a wavelength. So you're being told that lambda over 2 is 14 centimetres, and therefore lambda must be 28 centimetres. And so to calculate the speed, V is equal to lambda f, and you're told the frequency in part B of the question, the frequency is 2 Hz. I'll write that over here. And so you have to give your answer in metres per second as well. So lambda is 0.28 metres and frequency is 2, and that gives you 0.58. and it's in metres per second. 0.56, sorry, metres per second. If you had just written down 0.28, you got 1 mark. And I'm not sure if you get any marks if you use the 14. You may get 1 mark if you use the 14. I'm not sure about that.